It's really a pleasure to be here and to be able to have you to speak with. And I just want to start with a little poll. Is this too loud? It's too loud for me. So how many of you do data science and have customers who consume your results? How many of you actually do data science and produce results? How many of those, so which is a third of the people, I guess, how many of those consciously provide your customer with an error rate or an estimate of probability that any of the answers you give are correct? Okay, about half of the third. And who has customers that don't give a damn? Okay, so that's pretty consistent. So that's what I'm going to talk about here, is the knowledge with which people do the work and provide the results and consume the results. So that's the big story. I'm a database guy. I'm not a data analyst. I have been doing data integration, databases, all my professional career. And I started asking questions, so what is this big data analysis? And questions like, is this really a new paradigm? And by the way, it is, and I'm here to try to explain that. What's the role of data in this whole process? And you can see in a couple of slides why I'm interested in that. And the question of a talk which I gave at the University of Texas at Austin last week was, gee, what could possibly go wrong? Do you think anything could go wrong with this big data stuff? A little bit, okay. I hope to persuade, and then the answer, in my view, is data science. And I'm going to define it in my own way, just because I'm that kind of guy. And I'm going to define it in a way to address the previous question. And that won't come till the end. So if you want to leave early, you don't get to find out. So big data is hot. This chart came from earlier this week. Billions and billions of dollars going on forever. And it's hot in a lot of ways. Not only is the market hot, but actually there is, in my belief, massive potential for applying data analysis to a lot of very, very important problems. And in some cases, we're working with Harvard on Ebola. Some of the cases are urgent. They need solutions right away. So if we can provide precise, valuable solutions quicker, that's obviously better. And Gartner has said that they have estimated that 80% of all business processes worldwide will change within the next 5 to 10 years, all based on big data analytics. So it's big and it's hot. I was just at the White House last week, where one of the predominant policies of the US government and 45 other governments around the world is big data. So what's big data? I mean, how could it be a government policy in England and America when we really don't understand it? Well, the potential that it holds is pretty remarkable. We've already had some pretty good results. And it has already changed a very large number of already operating processes in healthcare, in manufacturing, in stock markets. You just search the web and you'll find these results. So it's already had a really big impact. However, it is not as widely used as one might think. So some statistics from ENC and Gartner and some others are, almost everybody's playing with it, and they're trying to put it in operations. But I can tell you in one very large company that will remain nameless but is in the telecommunications business, and I used to work for them, is they have little pilot projects trying to understand it. But would they put it into operations? That's a bit of a risk because they don't know what the consequences would be. And we're working at MIT with Mount Sinai Hospital and have come up with some concrete results on predicting when critical liver disease occurs in what population of patients. Have they put it into practice? No. It takes a long time to change processes in companies or hospitals. So the results on operate. Lesson one from the lecture that I'm trying to persuade you is data science, big data analytics is in its infancy. It's hardly gotten off the ground. We don't understand almost any of it. So it has massive potential. So some of the four leading, as I said, I was in the White House last week with the chief data scientist of the National Institutes of Health. His charter is data science for personalized medicine. And you can see here 200 billion, almost 200 billion in each of the four major diseases that the government, US government pays for. Okay, we can save money if this stuff works, but more importantly and more ethically, we can get more effective and faster solutions in healthcare if it goes the way we hope. Now, what could possibly go wrong with big data? So if you've been in the big data field for a while, you certainly know all of these silly correlations that people talk about. So that's the funny side of it. Unfortunately, it actually has happened in a great deal of cases, and happily they weren't very important. Google Flu Trends is the one you're probably all familiar with, and just to be very brief about it, the notion was that the CDC, the Center for Disease Control in Atlanta, does surveys on a slow periodic basis, weekly and monthly. So they can predict flu trends on a weekly, monthly basis on surveys that they've conducted for years, so they really know what they're doing. So Google comes along and says, hey, we got data coming from queries on a moment-by-moment basis, so we can be more precise, we can be spread right across America, we can localize to Atlanta, to San Francisco, and all those sorts of places, and we can get it faster. Unfortunately, they were way wrong, 100 out of 108 weeks. So fast? Sure. A lot of data? Sure. A lot of queries? Sure. Does it answer the question? It makes it worse. So that's... Now, it even gets more extreme than predicting flus going wrong. There is a foundation that was set up by people like Stephen Hawking, Bill Gates, Elon Musk from Tesla, who put together a charter which is now signed, you can find this on the web, which is signed by about 1,000 of the leading AI researchers in the world. And it simply says, let's make sure that artificial intelligence doesn't negatively impact humanity and life on our planet. And that's interpreted by the media as AI is going to kill us. That's literally what the BBC and other people said. Now here's an interesting response. The legal community in the United States, led by a professor at Harvard, a really wonderful guy, really imaginative guy, and NYU and some other places, they were about to promote a law under the title of algorithmic accountability. And the premise is, if you provide me a service, I don't care whether you got it from a machine or human or whatever, you're responsible. By the way, do you know what your algorithms do? And most people don't. So this is to demonstrate that this stuff about big data is serious. It is being applied in very important areas in our lives, and the legal community is seriously asking questions about its efficacy. So the question is, what can we prove about the stuff that we do? Do we know that the results we get out are correct, or complete, or efficient? The efficiency, of course, may not be so important from an ethical point of view, but it's only efficiency that has driven big data from the very beginning. The very fact that we can look at this data in really short times has brought this to life. So the issue that I'm concerned about is correctness and completeness. So do we understand what machine learning does? So let me give you an example. You know, how many variables can you get a PhD on? Does anybody here have a science PhD or know something? How many variables do you need to play with to get a PhD in science? 1? 2? It's getting probably not 3 and definitely not 4, right? Because the controlled experiments under the scientific method make things very, very complex to understand the interrelation. So humans tend to think in less than 10 variables. In fact, there's even a theorem that goes back to a sentence by a guy in psychology that says we can only keep 7 or 8 ideas in our head at any one time. How many variables does a machine learning algorithm look at the high end? Is it 10 or 20? Hundreds, higher, billions. So how can we possibly even understand what is going on? We get a result out. Whoa, that's pretty cool. But what does it mean? And what were the consequences? What were the priors that led to this pattern? So the pattern may be there. That's called what? But why is it there? Okay, I'm getting lost here. I get kind of excited and hot under the collar because, well, I'm wearing a tie too. But, so we are living in a society that's rapidly becoming data-driven. And there's extremely high rewards, curing cancer quickly, stopping Ebola quickly, helping poverty, all kinds of wonderful things that it could do. But the risks are equal. Because if I'm told that you need a particular medication, or you and your population need a particular medication, and I produce it and I give it to you, maybe it'll turn out like thalidomide. We have a whole generation of people who are crippled. So there is risk and reward. And we want to maximize the risk and minimize the reward. How did I say that? Oh, at least you're listening. This is good. This is good. So we're searching for truth. Right? There is no truth. Because truth is with respect to a system of beliefs or equations or something. So there is no truth. There are perspectives. So what do we use big data for? We want to find evidence-based causality. That this causes that, and I have significant evidence to find out in all the contexts that it's important that this does cause that. So where do we get that from? We get it from evidence-based correlations. How many correlations do you think you would get out of a machine learning algorithm that looked at massive data that might have, let's say, 1 million variables? How many correlations, significant correlations, would you get out? Ballpark. Millions. How could you choose which one to follow? So this is a challenge. So what we're playing with, so this is how the thinking process is. I'm walking over here. I'll come be over here for a bit. So this is a traditional way of doing science, or mostly science, but now it's gone to many other things. You have a hypothesis, and you look for data to see if there's a sufficient amount of data to say, yes, that hypothesis is true. Or if you're more ambitious, you say, well, I have a whole bunch of hypotheses. Oh, sorry. That's if data is true. That's that pink thing. So you say, well, I'm more ambitious. I have hypothesis 1, 2, 3, and 4. My son's doing a PhD over 3 variables. So I guess that's a theory. And then you similarly look for data to prove it. But this is all about analysis. So this is the big picture. The big picture is we're looking for evidence-based causality from evidence-based correlations. And most of the algorithms in machine learning and most of the stuff in big data produce far more results than any human could possibly consume. So we have to be able to manage that. So, how old is big data? Well, or how old is data analysis? Mathematics is about a 4,000-year-old tradition. I'm sure we're all aware of that. And the scientific method has about 2,000 years behind it. And over the most recent 1,000 years, it's gone through what are called 4 stages or paradigms. The most recent being declared by Jim Gray in 2007, called either e-science or big data, call it what you like. But that's the focus of this talk, this 4th thing down here. So, 4,000 years, 2,000 years, 1,000 years. How old is the stuff that we're working with? Well, we've had computers for about 60 years. We're just barely beginning to understand them, and haven't they transformed in the last decade? Right? So that's a big change there. Now, what about data-intensive everything? So I say data-intensive. I don't like using the word big data because it's been played around with a lot. So I say we're doing data analysis, but we're doing data-intensive analysis. And intensive is just to say it's big. Big in volume, big in whatever. Variety, by the way, is more important than volume, as it turns out. It's a harder problem to deal with. And this point about saying it's data-intensive analysis of everything, you need to be, I'm trying to make a very careful point here. For about 1,000 years, the scientific method was applied to physical phenomena, to what we call science. These methods are being applied to people reading English books and writing poetry. That is, these methods are being applied to every human endeavor. Is there a risk there? I think there is. Because if it's science and we can control the variables we're looking at, that's one thing. But if we transform into literature, art, social aspects of our life, To what extent can we control the parameters in which to apply the scientific method? So already you see there's a fundamental switch going on here. So e-science has been around since about 2000, big data since 2007. It's coming mostly out of the particle physics community, and of course those happy guys on Wall Street. And that's been around for 15 years. So I suspect that this new thing, whatever it is, we're only just beginning, and we've got at least 50 years to go. And I'll give you an example. Well, it's not here, so I can skip it when I come to it. A paradigm shift, according to Kuhn, who wrote the definitive book on the topic, is you have a qualitative difference in the concepts you use, the theories that support it, and the procedures you execute during it. And one example, I know a lot of people here in statistics, Stanford, Berkeley, and MIT, and I'm sure many, many other universities, have now created new departments. MIT was this summer, Stanford was, I think, spring. A new department devoted to what they call 21st century statistics. Can anybody guess why? It's not the statistics department, it's a new department. Why do you think that is? Because, well, I'm going to say, and I'm not a statistician, and if you are, don't shoot me, but the statistics that have conventionally been used and developed and are very sophisticated are known to apply to small data. As the data variety grows, as the data volume grows, we are not sure if the same statistical methods and metrics still apply. And I'm not a statistician, but Michael Jordan and some of the world-leading statisticians are, and they head these institutes. So what I'm here to tell you is, if you don't know already, the tools that we use in mathematical analysis break somewhere. We don't even know where they break. Okay, is that scary enough? All right, so let me give you an example of where I think we're going with big data and data analytics, data-intensive analytics. This comes from oncology. It's about a decade old. You take a biopsy, you sequence it in a machine, meaning you convert it to data. You compare normal cells with cancer cells. You look for anomalies. And having found the anomaly, and you know the pattern in the population, you then look for some sort of treatment that you can give it. You test out the treatment with a human being. You then make another biopsy and see if the cancer's gone away. This takes a decade. And they want to accelerate that. And they want to accelerate with big data. So I'm going to show you a schematic of the way I think it's going to go. And it's really kind of cool. The stuff on the left-hand side is the models. That's where the data is. You create a model, you go get the data, you populate your model with data, and you come up with, hey, I found something. Or in the case of machine learning, hey, I found a billion things. And so this is on the what side. And then you say, I want to figure out why these correlations arise. So you choose 1 or 5 or 10 or something. And you start to experiment empirically, and that's old-fashioned stuff. Nothing to do with data. And you're not going to get to the truth through the data without doing this empirical stuff. And then, so the way this goes is the model produces a bunch of correlations. You choose those with the highest probability of becoming real or being true. You then experiment on them, standard clinical trials, and they still take 5 or 10 years. And then you come out with a result. The result has got to be probabilistic because you don't execute the experiment on everybody in the population, only on a subset. So what's the likelihood that it'll work for the bigger set? We don't know. So here's the way we hope this is going to go with big data. So first of all, at any point in this cycle, start anywhere. Start with the experiment, start with data, I don't care. And then you get some sort of result, you give it to the model and you say, can you refine this model? So if you're a modeler, you might be sitting with a cancer expert and you say, well, I bet this implies that implies that, blah, blah, blah. All sorts of neat things. You change the model. You then produce some new correlations. You feed it through to an experiment. And this is where it gets kind of exciting. This thing here, generating models and correlations, any of you who do data science, you know you have to do it several times. Well, in the genetics world, they do it forever. They do it for years. running through these iterations to get correlations that appear to have high significance. But what's interesting over here, in the empirical world, the clinical trial world, they're also doing something called adaptive clinical trials. And that means you don't take the trial through to its end, because at some point during the trial you recognize one subpopulation diverts while one subpopulation converts on your hypothesis. So you don't finish. You throw away the divergent ones, you take the convergent ones up here, and you say, let's do this again. Let's refine it. Let's go get some data. And the belief is that this method of combining clinical trials with big data can accelerate drug discovery by a decade. I mean, by a factor of 10, from a decade to a year. And we even have some evidence of that. Has anybody heard about the Baylor-Watson result? So what happened there is they used Watson, the IBM text analysis engine, together with scientists from Baylor Medical in Texas. The reason the brain is here is this is an example of top-down. Where did the hypothesis come? It came out of wetware, somebody's head. That's one way to do it. And the other way to do it, those are Baylor scientists. The other way to do it is, it's called hypothesis generation. You look in the data for some sort of significant trend, and you say, okay, this is a hypothesis, let's go see if it's real. So it's some combination of these things that is our future. It's not all going to be all bottom-up. Doesn't happen. CERN does not do bottom-up data science. They do top-down. They have a model. It's called the Standard Model of Physics. Okay, been here a long time. Okay, why is it a paradigm shift? We're going from a small amount of data to a large amount of data with large volume, large variety, and so forth. We are shifting our resources from asking the question why to ask the question what. Quick answer, why would we be making such a shift? I mean, it's big data, that's what that does, but why is that shift happening so much? Easier, cheaper, more readily repeatable, and patients don't tend to die, except the guy in the IT department. So, and then it's strategic as opposed to tactical. We're moving from strategy where someone says, I believe that this implies that. That's my strategy, we're going to go look at it. And we don't do it that way when you go bottom up. Bottom up is tactical. We have evidence here that that implies that. Now let's go and prove it in a clinical trial. You can say exactly the same thing between saying it's theory-driven versus data-driven. Those are synonymous. But the interesting change here is hypothesis testing used to be what we did. I have an hypothesis, let's go find data to confirm whether or not that hypothesis is true. Now, in the big data world, it's generating hypotheses. We've got to choose which one seems likely and then go down that path. And I just want to be clear here. The diagram I showed on the previous page, I don't believe in either top-down or bottom-up. I believe in mixing the two in a judicious way. So these techniques are changing science. I don't know, how many here, are any practicing scientists? A couple. So since probably over the past 30 years, scientists went from dealing in wet labs with physical phenomena to dealing with data sets. My next door neighbor has been an astrophysicist at Harvard for 40 years, and she has spent the vast majority of her time not on a telescope, but looking at Fortran files. That's where she started. So almost all science nowadays is done over data. So that's where the world of big data is. So it is changing most domains, how medicine is being conducted. All the drug companies are buying machine learning people as quickly as they can because it's much cheaper to develop drugs using big data and automated techniques. And as I'm saying, I believe in a judicious combination of what and why using machine and human intelligence. So I have a lot of use cases that I have experience with, and I have never seen a use case that does not involve being guided by a human decision making. So here's my big picture, and I'm going to quote one of my heroes, Michael Jordan, one of the leading statisticians and certainly one of the leaders in big data analytics. And he was asked, hey, what's the cool new technology? And the answer is none of it. It's the pipeline. It's the end-to-end that's important. We've got to understand the whole system. So based sort of on this premise, I went and studied over 30 now really large use cases, and I'm going to try to summarize them for you. So here's lesson number 2. What was lesson number 1? That was only 2 minutes ago. Data science is in its infancy, okay? I'm going to come back, so you remember that, okay? So this is lesson number 2. And lesson number 2 is data science, or data-intensive analysis, is typically thought of, I have a model that I've created myself, I go get some data, I apply some analytical techniques, and I get a result. That's what it's typically thought of. Or down here, I have some data, I'm going to deduce a model, hypotheses are going to be inferred, apply some analysis and get a result. So that's typically what it is. And so that's called data-intensive analysis, and that's sort of the scope of data science as it's typically looked at. I'm here to tell you, this is perhaps one of the main messages of the talk, this is not the case. It's part of the story, of course. This is the part that I do. I do data stuff, and it's not because I do data that I'm making this big. It's because I've gone through 30 of the largest use cases in the world of applying data-intensive analysis. And 80% of the resources, 80% of the skills, 80% of the time take place doing these 2 things. Finding the raw data in the first place, selecting it, preparing it, curating it, and storing it and making it available for analysts, whether they're financial, physics, whatever it happens to be. Now that the data is in this big repository, we have in CERN, how many scientists are there using the data at CERN, roughly? 2, 3? 10,000. There are 10,000, and they all have their own groupings of experiments grouped in about 7 to 10 people. And so what they need, each one of them needs to go to the analytical data and acquire the data for their particular model. And if you're looking for a top quark, you don't want all the data at CERN. You only want those events in the database that pertain to the hypotheses that you're looking at. And if it's top quark, you may be looking for 3. So you do a filter here, and now this analysis starts. So what I'm trying to tell you is data science isn't just the analysis part. That's very important. Data science is the entire range from getting the raw data to producing the results. Okay, that's number 2. What was 1? Infancy. Good, good. We have to get a word for number 2. Data. No, that's not good. So, and also, what is big data analysis or data-intensive analysis? People often say it's extracting knowledge from data. That's trivial. It's like gardening is taking a shovel and digging dirt out and then putting something in, putting the dirt back. I mean, the point is you garden to get food or flowers, right? So really what we're doing here is it's an activity of using data to investigate a phenomenon. So that's for sure. And we want to acquire, so that we already have knowledge about whatever it is, otherwise we would be asking questions. So we want to acquire new knowledge, and we want to integrate that knowledge into the knowledge we already have. So I don't know if you recognize this definition. This is the definition of the scientific method. So my perspective is data science is data applied to the scientific method. It's what scientists have done for 50 years, but now the data's getting into an interesting place and they need our help. So the workflows that I'm interested in are the sequence of operations, all the things you need to do to go through the whole process. And you're probably not interested in all of them. You'll be interested in those that relate to your expertise. Okay, let's move on. So I looked at about 30 use cases, and I want to share some lessons that I learned from these use cases. And these are the standard use cases that occur in business. Customer analysis, fraud, compliance, and impacting customer relations. I didn't look at any of those. I'm not interested in those. I'm interested in use cases that are so big and so complex that they push the limits of our tools, like statistics, like databases, like processing. Why? Because when you see these examples, you don't push the limits of statistics very often. You don't get into the problems. I'm looking at what are the future problems facing data science that we're going to have to address fundamentally, in terms of theorems, procedures, and so forth. So I'm not looking at these guys at all. In fact, I characterize data analysis as being the stuff that we've done. 98% of data analysis in the world is the old stuff. This new stuff hasn't caught on at all yet. Just put it in perspective. It's conventional analysis. We've done it for 1,000 years with databases, spreadsheets, all sorts of things. Everybody's really familiar with this. Our world runs on this stuff. Now let's go to big data. Big data is around 2% of all computation and all data analysis done in the world. Not a lot. I mean, it's growing, and I'm not trying to diminish it, but in practical fact, it doesn't get used a lot. It's new. And out of that, there are two classes. There are what I call the simple data-intensive analysis. The two spreadsheets I showed you earlier, the things that happen in companies, those are simple. They tend to have relatively small amounts of data. So it's simple models. And do I have his name here? I don't. Oh, Jeff Leake. Yeah, so Jeff Leake. So Jeff Leake, one of the leading data scientists in biology and in the United States, gives MOOCs, and a very, very smart guy. He says, if your model's complex, you're not doing it right. And there are many, many cases. In fact, the vast majority. I'm interested in the big ones. The big ones where the domains are very complex. The economics of an entire country. The energy flow of an entire country. Water. Genomics. The human body. Those things. So why? Because they are real. They exist today. I've looked at 30 of them. And they push the limits of pretty much everything we can do. So that's what I'm trying to... Oh, and just to give you an idea, these complex things, this is an example of a small one from Harvard. This is a scientific workflow. And Claire, the woman who I'm going to refer to, got her PhD at CERN last year in high-energy physics. And it was her that I spent most of my time with, understanding how CERN processes their data. How long do you think it took Claire to do her workflow and to get her experiment running at CERN? You know, it's not you push a button and it comes out. So how long? Was it a day, a week, a month? 2 years. It took her 2 years. And in all the cases I've looked at, Novartis, Thomson Reuters, all these big companies, this data analysis, it takes years to put the model together. Years. Okay. Let's look at CERN. Everybody knows CERN, right? Everybody knows what goes on. So we have an accelerator. And we have about 4 or 5 experiments, each of which has its own detectors and algorithms and processes. And they look at a proton-proton interaction, and they look for events. So how did the Higgs boson get discovered? Well, in 1967, Peter Higgs and 3 others simultaneously hypothesized the existence of it. And you don't need to except you have to memorize these. Okay? Everybody else, you're good. But these are the characteristics that it took them 30 years to determine if we do have a boson, then under an energy interaction like foobar, this is what we would expect to see. So first of all, you've got to develop your model of whatever it is you're analyzing, and it's very complex there. Okay, now, remember I said being correct and complete. So we need... Does the boson exist? Is it correct? Yes or no, it does or it doesn't. Is it complete? That is, should it have been something else? Is it at a different energy level? Does anybody know the story? This didn't happen overnight. Like on July the 4th, 2012, when they announced, both Alice and CMS, when they announced their result, it didn't happen overnight. It took 30 years. So the first 30 years to develop these characteristics, about another decade to develop the design of an experiment. So that's what you need to do in data science. You have to have a hypothesis, you need a method by which you're going to test it, and you need criteria for whether you found the correct answer or not. They then spent a decade building the accelerator. They then ran the tests, and then the 2 separate experiments and it provided their answer. Neither experiment saw the other's answer. Why is that? All of this is important for data science. These scientists discovered a major part of physics by doing big data analytics. The reason was they needed to be unbiased. So first of all, it took 30 years to put the model together to figure out what the Higgs boson would look like. Then it took a decade or 2 to design the experiment and run and get the data. Now they're going to do the data analysis. They did the data analysis, 2 completely separate groups, and they hit 5 sigma, that is 5 standard deviations. That is, here's the answer, and the next most possible answer is 2 million% away. So that's anyway, I'm going through this in terrible detail because when you do data science, you have to do something like this. There's a question you're asking. You have to have a model that you can replicate the data in. You've got to get the data. Getting the data is complicated. I'll tell you a bit about that. You've got to clean it, prepare it, curate it, select it, ensure that it's random, ensure that it's representative of the population you're looking at. This is complicated stuff. And you're not doing particle physics. But when you're doing a marketing study or when you're doing some other data analytical thing, the same rules apply. And guess what? Modeling is no easier with big data than it ever was before. And if you've done any modeling, you know modeling is not easy. So in CERN, the data comes out of the accelerators and they do all this work. There's 3 levels of curation and cleaning and storing and selecting. And at the same time, they are generating the exact same data out of the hypothetical standard model of physics. And you've got to do this, again, to avoid bias. That is, you've got to run the experiment in such a way that how do you do it on all your assumptions, and how do you do it with the real data, and then you have to switch them. So it's complicated. Now, again, the data science you guys normally do probably isn't this complicated, but the errors that we find in these processes come back, and that's going to be the theory to underlying data science. Why is this important? Because our society is becoming increasingly data-driven, and we don't want these computers screwing up. The architecture of their system is they clean the data, they put it into a repository, and there are about 1,000 experiments going on, each of which selects data selectively for their particular thing. So that's the way that works. So there's 3 processes: get the raw data and get it ready. The next one is acquire the data for your experiment. And how am I doing for time? 7 minutes. Oh my God. And then the analysis itself goes on out there. And most people think of only the analysis. That's 20% of the work. This stuff here took a decade. This stuff here took a few months because of computing processing power. And they spent 10 years from 1993 preparing root and all this other stuff in order to do the running. Okay, now they spread this data over 200 sites around the world. So this isn't of interest to you, but it is to me because I'm a systems database guy. So this is the architecture of future data science systems, where there's a source of data, it's curated, put in a repository. People call it data lakes these days, but it's a stupid term. And then they spread it around the cloud so that people can use it remotely. So this is the general architecture that's arising. Lessons learned. A data-intensive analysis is a piece of software. It is predominantly a data management activity, but it's partially analysis activity. And we don't like this. I advise a company that does data curation, this sort of stuff for scientists. We're trying to flip this so that by the way, the scientists do this work. The guys at CERN, there's a whole team of people who are scientists. They shouldn't be doing plumbing, they should be doing science. And this is the case in every industry. Manufacturing, doesn't matter what it is. Cleaning up the data is a mess. These data-intensive analyses, they're software, but not like the software we're used to, where software engineers build stuff for, that you punch and use. Data scientists build stuff so you can play with it and run it, it breaks, run it again, it breaks, run it again. So it's a very different method, it takes years. So we have an emerging new paradigm. Almost all these paradigms of databases, database query, information retrieval, business intelligence, data mining, they're all converging around these data methodologies I was telling you about. So there's a new programming paradigm, and that's kind of cool. If we can't read that. Well, what were all those things about the boson? No. So the results that come out of high energy fit or anything, if you have enough hypotheses, that is, if you have an experiment and I say, I have the hypotheses that I'm trying to test, and I know how I collected this data and what I did with it. I know all the hypotheses, and then you get a result out and you hit 5 sigma. In science, you have a causal result. That's been the case for 300 years, shall we say. Oh, so that we know that. So there are results that are provable if you have the metadata that allows you to make the conclusion. In big data, that's almost never the case. Try to get your friend's metadata who's giving you the data. So we are dealing with things that are probabilistic. And how do you measure the probability of any outcome? Well, our statistical techniques, folks, break. We don't know. And as we heard earlier in an earlier talk, science and nature have given up on, not given up, are warning scientists worldwide that p-values, the typical notion of measuring significance, are no longer usable. And a journal in psychology will not publish any paper that is dependent on a p-value. So we need to think that out. Okay, I'm going to go fast. Claire was an individual at CERN. When she developed her experiment, she went and spoke, got it approved by a working group of 7 professors who oversaw her work. Once that group approved her result before she ran her experiment. By the way, here's something amazingly cool. Once she got everything worked, she only had one chance to push the button and run the experiment to get a result. Why? Bias. So let's say she ran and said, oh, I forgot that. And you run it again. Biases come in. If you get to change something and say, oh, I didn't mean that. You change it. So you have to be careful about the assumptions you make when you do data science. You have to be honest and clear with it. Anyway, once her group approved it, it went out to the entire Atlas program and they accepted it. And once they accepted it, they published it in the physics world. So this also happens in companies, where there are small groups that do experiments and it goes out the company in an authorized way. You have to combine machines and humans. Everything's multidisciplinary, collaborative, and iterative. And that thing I showed you about Claire and individual group and so forth, the cost of putting this stuff together. So Amazon is kind of the cloud at Amazon is probably an easier way for everybody to get resources. But in general, you need a lot of resources for storage, for algorithms. You need knowledge too, and you need to collaborate. So there are now what are called science gateways, e-science, science gateways, network science. There's many names for them. And there are 60 very large ones around the world. And that is like CERN. They provide the basis on with which to do this really large big data analysis. And I think we'll find it in genetics, in manufacturing. That is, manufacturing companies collaborate to establish a competitive basis that is fair, but more advanced. So this is what's happening. So we don't have truth. Oh yeah, so what are this is one of the biggest lessons learned that I got out of this, and that is, there is no truth. We want to get evidence-based causality. It comes from correlations. So the question is, how do you ensure that the question you're asking gets the right data to provide significance to say, yes, it's causal? We don't know. In general, we don't know. So I guess I'll skip this use case because I've only got a minute left. But this use case is a very large Reuters, Thomson Reuters, Dow Jones, companies that process information. They've been doing it for years, 40 years. And so their models for these things down here, they don't have to invent those models. They've had those models for years and years and years. What's new is massive amounts of data. They look at the stock market closes, the SEC filings, legal filings. Now they're looking at data from 100,000 data sources to improve the veracity and value of the results that they sell. But in addition, they add legal opinion on top of it. And what happens if they make a mistake? They could, like if I'm a company and I go to one of these Thomson Reuters or somebody and I say, I would like to know all the information about Siemens because I'm thinking of buying Siemens. And I trust them, I buy Siemens, and something was wrong in the report. You know, the opinion was incorrect, and I lost billions of dollars by buying Siemens. I could take them to court. There's a legal liability. So I just want to say that being wrong in big data, either you screw up physics, but the physics world wouldn't let you do it, or you screw up business, and the business world is not going to let you do it. Summary slide, summary slide. Oh, are there people here who do data mining? No, some, not a lot. Okay, I'll skip this part. What do I do? Sorry, don't look. There. More lessons learned. I do modeling. And the analytical models that people use, so I'll give you one example. At the moment, the United States is taking a very big political step and negotiating with 13 Pacific Rim countries on what's called the Pan-Pacific Agreement, which is a trade agreement excluding China. It's a political thing. And the White House that's promoting this has said, here's the economic results of it. It's going to be really great. And the Republicans come out and say, these are the terrible economic things that are going to happen. The world's going to fall apart. And so what economists have done is they've looked at the analytical models that the Republicans used and that the White House has used, and they find that both of those or have their origin in a United Nations model, economic model of the world based in 1940. And so they're both wrong. But what I'm trying to tell you is you don't do data science without some sort of significant analytical models. And let's say I wanted an econometric model right now because I wanted to do analysis. Not hard. There is a database of 100 of them out on the web. And if I happen to like Thomas Piketty, the rather famous French economist, you know Thomas Piketty? Oh, gee. Maybe Switzerland, everybody's rich and they don't listen to people like Thomas Piketty. Okay, so anyway, they're available. I can go and get them. But which one do I use? Which econometric model do I... So let's say I choose one. How do I tailor it to the hypotheses I'm looking at? And how do I find the data? So Piketty and a professor from England went for over a 10-year period and got tax and income data from all over the world and put it in a database, and by golly, you can go get it. But there are gaps. So how do you fill the gaps? Okay, so it's complicated. So number one, modeling is hard, and the data models, I had a discovery, and if you're interested in databases, schema integration is a real pain in the ass, and I have found, after doing this for 30 years, that if you model the entities quite separate from the relationships, you solve a lot of problems, and that's why I'm proposing for data lakes. You heard it here first. And so to show you that it's in its infancy, there's hundreds of models, of pieces of software to do all this stuff. Entire ecosystems, languages, they're coming up all the time, just to reassure you that this is an emerging area. So what could go wrong? You saw this slide at the beginning. Professional organizations around the world have come out and said, hey guys, be very careful about what you're doing. The OECD came out and told, where is it on here? The OECD came out and told the national standards organizations of the world, be very careful in using data to enrich your normal surveys, because you then predict certain economic trends, and those economic trends are used by ministers and other people to change policy in countries. So don't go screwing around with it unless you really know what you're doing. Mount Sinai Hospital won't accept our results because they don't want the whats without the whys. And the legal community is now closing in. So what could possibly go? I've only got a minute, right? So, well, -2. Oh. Well, so I'm trying to tell you from the data side. Let's assume that you assume that data analysis is all of data science. I'm here to show you that on the data management part, those two things that I said were new to most people, is the data sets can be wrong. The models you choose to store the data are wrong. The methods, how many statistical methods might one choose to analyze your data? Ballpark. About 10,000. How do you choose one over another? Well, you have to know the skew of your data and whether it's dense and the nature of the data and the kind of errors that normally arise in that domain, blah, blah, blah. It's complicated. I guess I'm going to come to the, I'm sorry, this is way too long. I'm going to give the, oh, no, that's not good either. No, this is what I think data science really is. You want a really smart flashlight to say, I want to find my keys. I think they're over there. And then you walk over and you look over the whole area. Data gives you a direction and a probabilistic estimate, hopefully, of what might be true. I'm going to get to the end. If you all look away, aha, this is my answer. Data science is the scientific method applied to data. So it is a body of principles and techniques for applying data-intensive analysis to investigating phenomena, the thing I said before, with measures of correctness, completeness, and efficiency. So I and my group and others at Berkeley and Stanford are beginning to work on the theory of data science based on this definition. You can define data science in many, many ways. I couldn't. Everybody should do what they like to do. But I want to be very concerned about correctness and completeness. So data-intensive analysis is an experiment over data. The value of evidence is clear. That is, it's really important. It's not the value of data. Data is data. It's only important if it's evidence for something. And infancy, right? Good. And there's a need for data science because we don't know what we're doing, but don't tell anyone. Thank you.
That was a wonderful talk. I think we will re-invite him for the third workshop on data science so we get the rest. And
I'll have the answer by then.
I have good news. So the slides will be available eventually on the website. So you will have a chance to look through all this stuff flying by us. We are quite advanced in time. So
sorry.
That's okay. Is there a pressing question? You're all overwhelmed. I can tell. So, there is one.
Brodie, MIT.
And maybe the next speakers can set up in the meantime.
So, I have a question. Since you said you worked in databases, databases is also my art.
Now you're a good guy.
I'm a good guy, thank you. And so, one of the big problems is also data integration, and you said now I've seen that you're also advising the Tumblr guys, and they do machine learning-based data integration. Does it really work?
Does it really work? We're making millions of dollars. Does it work? So, the question that was asked, I have years and years, 30 years experience in data integration. Look up all my papers on the web. Don't read them. There's no value. Because in the database world, we would take two schemas that describe a state of the world, the generic state of the world, and try to put them together. But they're put together by people who have different views. And so you have to do some crazy stuff, and you always make a mess of it. So I think you're referring to the fact that discovery that I had in looking at data lakes and big data analysis, and Novartis, Thomson Reuters, Twitter, Pinterest, LinkedIn, they store their core entities in what I call a data lake. And in LinkedIn and in Facebook, they want to have all sorts of what they call a graph model. So there's one guy has a model about how people interact, and another guy has another model. So they completely separate the semantics of the entities from the entities. They're raw entities, and we model how we think of the entities in independent ways. We don't ever have to integrate those, because they're separate points of view. So this is what I'm about to do more research in, because it seems to make a lot of sense. Does that answer your question?
Okay.
Okay.
So, thank you very much.